Computer Science and Engineering Colloquia features accessible talks by leading computer scientists and computer engineers from across the region and around the world.
Hello, everyone. Welcome to CSE Colloquium. Today we have Joseph Gonzalez. He's finished his PhD from CMU. He's been a postdoc at AMPLab at Berkeley for the last couple of years. He's doing a bunch of really interesting work at the intersection of distributed systems, operating systems, databases, machine learning, big data, all kinds of different things. He's published in the premier systems conferences such as OSDI, in database conferences such as CIDR, as well as NIPS and other machine learning venues. And in the last couple of years, he's been working on building systems which have been pretty popularly used. One such system is GraphX, which basically integrates graph processing with traditional data parallel computing. And he's going to tell us much more about all of that stuff soon.
Cool. Thank you. I'm excited to be here. It's an honor. I'm also a co-founder of GraphLab, which we had to rename to Datto. Word of warning, if you start a company, think of your name carefully, because you might have to change it, especially if your research changes. So my research changed. I started studying machine learning. I ended up studying kind of systems and how machine learning come together. So today I want to talk about my work in learning systems. It's really the study of systems and abstractions for large-scale machine learning. Let me begin with some motivation. The world of machine learning has changed, especially when we think about the scale and complexity of data. It used to be that 10 gigabytes was a large data set in machine learning, and in some venues it still is. But more often than not, we think of data sets as being much larger. Things like the YouTube video data upload rates in the order of 72 hours of video uploaded every single minute. And these companies are actually trying to apply machine learning to these huge amounts of data. Then we think of complexity. It used to be we think of data as largely independent, processing independent records. But now we think of data as deeply dependent through social networks or through graphs that relate to things we're trying to reason about. And then when we think about the architecture on which we compute, it used to be spinning disk hard drives and single processor architectures. But now we're presented with SSD drives and a wide array of parallel and distributed processing resources. And so this leads to an important question. How can we take these advances in parallel hardware and apply them to the important big data problems we want to solve in machine learning? And my approach to this is what I call the learning systems approach, which begins by thinking about the design of scalable machine learning algorithms that address these large problems that we want to be able to solve. And then by identifying common patterns in those algorithms, we introduce abstractions that capture the structure of machine learning and allow us to build scalable systems to execute those abstractions at scale on these parallel and distributed architectures. And so I believe it's important that we look at all three aspects of this. That if we were just to focus on the design of scalable systems, we'd build systems that fail to leverage the structure of machine learning algorithms. Alternatively, if we were to just to focus on the design of scalable machine learning algorithms, we'd build algorithms that ignore advances in system design. And then if we were to try to ignore abstraction, as I did early on in my research career, we'd build algorithms and systems that are overly complex and difficult to debug and extend. And so I believe it's essential that we look at all three aspects, design of algorithms, abstraction, and systems jointly. My research has really spanned the space of learning systems. Early on as a PhD or as a graduate student at CMU, I worked on the design of scalable learning algorithms for graphical model inference. Then as a postdoc, I started thinking about how to build scalable algorithms for modular optimization and non-parametric inference. Building on the common patterns in these algorithms, I designed abstractions like GraphLab and the parameter server, which capture that structure of computation, and then allowed me to build systems like PowerGraph and GraphX that can execute those abstractions at scale, often orders of magnitude faster than contemporary systems. So that's the work I've done in the space of learning systems. We can kind of lay this out in the modern learning systems landscape. So I've divided the space of learning systems today into three main categories. We have data flow systems like Hadoop and Spark that operate on largely independent records. We have graph systems like GraphLab and Giraffe that operate on large graph-structured data. Then we have distributed shared memory systems like Ptuum, the disk belief network, and the parameter server that allow us to operate on these large models and things in the context of deep learning. As we think about my work in the context of algorithms, I really focus on the design of algorithms for graphical model inference in the context of graph processing systems. And then later on in the design of non-parametric and submodular inference techniques in the context of distributed shared memory systems. If we think about abstractions, my work really helped define the fundamental abstractions for the execution of graph algorithms in machine learning and data analytics with the Vertex programming model. And then I played a key role in defining the parameter server abstraction, which is now used in a lot of these parameter server-based systems. And then finally, if we think about systems, my core focus or core contribution has been in the design of the GraphLab system, which has enabled us to take these Vertex program abstractions and execute them on multi-core and distributed architectures. And then as a postdoc, I went back and asked, how can we connect these graph systems to these more general data flow systems? And I introduced the GraphX project, which allows graph computation to live in a data flow framework. That's kind of an overview of my work. And I want to focus today on the story of learning systems, or of graph processing systems, as it's emblematic of this learning systems approach, spanning the design of algorithms, abstractions, and systems. But before I do that, I want to first motivate the importance of thinking about graph-structured data. So why do we study graphs? We study graphs fundamentally because they provide context to our data. They allow us to think about uncertainty not in isolation, but through its relationships. And these relationships are a critical form of signal that allow us to deal with very noisy data. So let me give you a simple example. Suppose I'm running an online social media service, and I'm interested in trying to predict the political bias of my users. Using traditional machine learning techniques, I could build a classifier that looks at each of their posts and then tries to infer the bias based on the text in those posts. So the user on the left here has 3 liberal posts, and the user on the right has 3 conservative posts. Now notice, for not all those posts have enough signal for me to make a prediction. Now, applying these basic classifiers to the text, I could reason about the users and say that maybe this user on the left is a liberal, this user on the right is a conservative. And for the users that I have these polarizing comments, I could infer their political bias. So using very basic machine learning techniques, I can infer the bias of the users in my service if they have that local signal. But unfortunately, the vast majority of users probably don't have these polarizing comments or don't post often enough that I can make predictions about their individual political bias. And so if I don't think about the connections, it's very hard for me to proceed to infer the bias of my users. Fortunately, I often have a form of side information, such as followers or retweet networks, that form a graph that allow me to reason about the users not in isolation, but with respect to their community. And exploiting this prior knowledge that something that the community I follow tells me something about my political bias, I can use machine learning techniques and graphical inference algorithms to push information across this graph and infer the bias of users for which I had little or no local signal. And so these graphs are pretty powerful, and they're everywhere, not just in social networks, but as we think about the relationships between items, the things we might want to sell, and the users that we want to sell those items to in product recommendation networks. Or as we think about images and the kinds of items we find in images, a similarity between the objects we're trying to recognize. In science, these graphs encode the structure of proteins or their side chain information. In literature and in language modeling, these graphs can form citation networks or co-authorship networks that allow us to reason about the relationships between documents. And in medicine, these graphs describe things like protein regulatory pathways, which are critical to understanding processes like cancer. So these graphs can also be very big. So we think of these graphs, they often have billions of edges, and they can have rich metadata. It's important to remember that it's not just about the structure of the graph that we're trying to reason, but it's also about the properties attached to the vertices and edges in that graph. And so these big and ubiquitous graphs present unique challenges to the design of scalable learning systems. When we think about algorithms, we're going to have to find ways to parallelize these dependent tasks and address the non-uniform convergence that emerges because of these highly irregular structures. When we think about abstractions, we're going to have to find ways to concisely and efficiently express our algorithms on these graphs and be able to encode this computation in a way that we can build systems to execute it. When we think about systems, we're going to have to find ways to partition and execute these computations across these real-world graphs that often have power law or highly skewed degree distributions. And then as we step back and think about how graphs live in the context of modern analytics, we're going to have to deal with the challenge of integration. So how do we integrate computation spanning multiple views of data, not just graphs, but also tables? And today I want to talk about how I address these challenges with the learning systems approach. In particular, I'm going to begin by looking at the early work in the design of graph learning algorithms and identify really the common patterns and unique challenges that these graph learning algorithms present to the design of systems. And then I want to think about the abstractions that we built to address those challenges, to capture those patterns, and the design of the GraphLab system that we use to execute that abstraction at scale. And as I said earlier, I'm going to step back then and talk about that final challenge of how we integrate computation spanning tables and graphs with the GraphX project. And then I want to conclude by looking forward to the design of interactive learning systems and how we can support machine learning beyond the process of training models to serving and maintaining models continuously. So let me first talk about the story of graph learning algorithms. And here I really want to identify the common patterns that emerge as we think about machine learning on large graphs, and the key system design challenges that emerge as we try to address these patterns at scale. So in an earlier picture, we're trying to reason about the political bias of users. We actually could frame this as a graphical model inference task, where these posts that we observe of these users are really observations of their unobserved political bias, these random variables in white. And to define a model, we're going to introduce potentials and code the conditional probability of observing a post given the bias of the users, as well as potentials that relate these unobserved quantities with respect to the retweets or how closely these users follow each other. And then this forms a joint probability distribution, a probability over the political bias of all the users in my social media service. And then the inferential question, the thing I want to build a system to answer, are questions like what's the probability that any given user is a conservative, so this marginal estimation task. Now, answering this question in general is NP hard, and so early on in my work, I looked at two standard techniques for solving these kinds of inference problems. So rather than give you the details of the algorithms or the math behind it, I'm going to give you a cartoon picture of how these algorithms work, and it will hopefully be enough to define the kind of patterns and challenges that we'll need to address as we build these systems. So we think of belief propagation, one of the first algorithms I looked at. It's a very simple algorithm in which we try to reason about the bias of a particular user by exchanging messages and coding my best estimate of my political bias with my neighbors and then receiving messages from them, and repeating this process until I've computed a good estimate for my political bias. Another algorithm, the other one we looked at, was Gibbs sampling. This is a simulation-based algorithm in which I assign a political bias to each of my users. You can think of these as coins. And then based on the current assignment to my neighbors, I draw a new assignment for my own political bias. Again, conditioned on those current assignments. And I'll again repeat this process, and the sequence of coin flips will converge to a stationary distribution encoding my marginal bias. Now, in both these cases, we have this neighborhood structure of computation, that I can really define the computation with respect to a vertex and its neighboring vertices, that it decomposes over the structure of the graph. And that's going to become critical as a way to build a parallel algorithm. By defining this stencil-like computation, I can then run it concurrently on multiple vertices, exchanging messages, or flipping coins concurrently in the context of Gibbs sampling. And so that becomes a way to build a parallel algorithm. And I'm going to iterate this process until convergence, until my messages converge or until my sampling distribution converges in the context of Gibbs sampling. So early on in this work, we started to ask, are these parallel algorithms efficient and correct? And so let me address each of these in turn. So we think about efficiency. If we go back to our story of belief propagation, we often found that a subpart of that problem would converge slower. It would take many iterations of that subproblem in order to reach a convergent condition. And so as a consequence of these slowly converging subproblems, we started to explore ideas in adaptive parallel scheduling, ways of applying processing resources to the slowly converging parts to ensure that we have fast, uniform convergence. And in this process, we started to also understand the kind of parallel scaling guarantees that these models present, both as a function of their structure as well as their parameters. And then when we think about correctness, if we look at the Gibbs sampler, it's tempting to try to concurrently sample all of these variables at the same time. But one can easily show that if we take adjacent variables and sample them at the same time, it'll actually converge to the wrong stationary distribution. This would be an incorrect algorithm. And so at this point, we started to explore ideas in graph coloring and neighborhood locking protocols to automatically ensure a serializable execution and therefore ensure that this converges to the correct stationary distribution. And through that work, we again began to understand some of the structure of computation. In particular, we could characterize the acceleration and ergodic mixing of these processes as a function of number of variables, the number of processors, and the number of colors in our graph. So it's taught us something about the structure of Gibbs sampling on these models. All right, and so in all of these examples of Gibbs sampling and belief propagation, we had these common patterns of neighborhood-centric computation, iteration until some fixed point condition is met, non-uniform convergence, and these consistency requirements that we needed to enforce. And what's remarkable is it actually turns out this is a general pattern in machine learning. It's not just belief propagation and Gibbs sampling, but many other algorithms share this common pattern. Things in structured prediction, community detection, collaborative filtering, semi-supervised machine learning, and even centrality analysis all have many of these similar properties. And so early on in 2009 at CMU, we began to ask, how are we going to implement these graphs in a distributed environment? And around that time, the answer, of course, to all things parallel was Hadoop, or MapReduce. And so what does MapReduce look like? It essentially means we take our tasks and we divide them evenly across our processing resources, compute in isolation, computing some statistic that then we aggregate to compute some final value. Now, if we contrast that to graph computation, it looks very different. We have these tasks that are now dependent because of this graph structure that are going to be challenging to partition across our processing resources. The result we're computing is not a single statistic, but properties associated with our users, our vertices, and our edges in our graph. We have this iteration and non-uniform convergence and these serialization guarantees that we needed to enforce. And so this picture on the right looks very different than the picture on the left. But of course, like everyone else at that time, we tried to squeeze the picture on the right into the picture on the left. And in some cases, you can do it, although it's very complicated, it can be very, very painful. And it's often highly inefficient. So at this point, we started to abandon Hadoop, and we returned to kind of our scientific computing friends and asked, what are other methods for building these scalable graph computations? And what they were using at the time were kind of low-level primitives like messaging and threads. So we picked that up, and we were able to build very fast systems, incredibly fast systems on top of these low-level primitives. But it also introduced a key problem. And that is the problems of low-level design. We had machine learning experts, or usually just me, repeatedly solving the same scalable system design challenges. I had to implement and debug some complex distributed system with each paper I wanted to write. I then tuned that for some specific distributed environment, one at the EC2 or at the Intel cluster at CMU, and then again on Amazon EC2. And then my paper, my evaluation, would end up conflating the system and algorithm properties. I'd go to a conference like NIPS, and they go, well, that's great, but is it the system or is it the algorithm? What was the contribution of that work? So we had coupled these two pieces of our research. And so the resulting code was also difficult to maintain and extend, again, because we coupled the algorithm and the model design. So what we see now is that we had these common patterns that span a wide range of computation that doesn't really naturally fit into this MapReduce model. And we had this need for kind of high-level abstractions and a system to execute those abstractions for those patterns at scale. And so that really motivated us to think about the design of tools for large-scale graph computation. And so now I want to talk about the abstractions that we built and the systems we built to execute those. So here the question is, how are we going to design an abstraction system for large-scale graph computation? And our answer to this was GraphLab, which in many ways was a MapReduce for graphs. So building on that analogy, if you think of MapReduce, we operate on collections of independent records. So our data model consists of independent records. Our programming abstraction is built around user-defined map and reduce functions, a functional approach to the representation of computation. And the execution semantics of MapReduce are built around this bulk synchronous model in which we compute all of our map tasks in parallel, and then compute the reduced tasks in sequence of bulk synchronous steps. And so you'd have to ask then, for graphs, what's the corresponding data model, programming abstraction, and execution semantics? And so for GraphLab, the data model we introduced is built around the property graph. And so the property graph is a very graph-centric way of thinking about graph-structured data. You have a very large graph representing perhaps a social network with user-defined properties attached to each of the vertices and edges. These vertex properties could be things like the user's profile information, as well as the current page rank estimate, so program state. And then the edge properties, again, could be things like weights, timestamps, as well as things like Lagrangians, or again, parts of the program state. And so this becomes a natural way to express both the data we're trying to reason about and the state of that computation. Now, to define our actual algorithm, we introduced a new programming abstraction that was really built around this vertex-centric notion of computation. Particularly, we introduced the vertex programming abstraction, which expresses these vertex programs in a sequence of functional user-defined functions that are gather, apply, and scatter, which are sort of analogous to the map and reduce and MapReduce. So let me explain how this vertex programming model works. Essentially, this vertex program is built around this notion of decomposition around the graph structure, where a vertex program is a program that describes a change in the vertex property as a function of the properties on adjacent vertices and edges. And we express this program in a sequence of gather, apply, and scatter stages. In the gather stage, a user-defined function g is applied to each of the adjacent edges and vertices to compute some statistic, collecting information around that vertex. And the user-defined aggregate, the sum, is used to combine those to compute some final statistic describing the neighborhood of each vertex. Then, having computed that for each vertex, we enter the apply stage, in which a user-defined function a is used to combine the resulting statistic with the vertex property as it is now to compute a new vertex property. And then finally, in a scatter stage, a user-defined function s is applied to each of the adjacent edges with the new vertex property value and is used to update these edge properties, perhaps to update Lagrangian values in some constrained optimization. So at this point in my talk, a lot of people had asked, what can be expressed in this decomposition of vertex program, right? And so actually, if we go back to this vertex programming model, we can express quite a bit in this gather, apply, scatter decomposition. Let me show you a hack that you can do. So if I take my gather function, and I simply return the property on the adjacent vertex and edge, or vertex and edge, and then I make my summation operation a user-defined aggregate, the set union, then the result of this gather stage will compute a statistic describing entirely the neighborhood of that vertex. And then in my apply stage, I can apply any computation that would operate at the level of a vertex and its neighboring vertices. Right? So this captures that vertex-centric model, but you'll see actually this could be very inefficient. So if we look back, well, this is a commutative associative operation. It actually means that the result of that gather stage grows linearly in the degree of that vertex. Now, we can execute this in our system, and we can express this in the abstraction. But in order to get an efficient execution, we're going to require that the aggregate be sublinear or ideally constant in the degree of that vertex. So this is how we're going to get efficient computation. We'll come back to that when we start to talk about the design of the system. All right, so that's how we express computation. And then the final question is, what are the execution semantics of a GraphLab program or a vertex program? And so in GraphLab, we actually support both a bulk synchronous and asynchronous execution semantics. And critically, we introduced this concept of dynamic scheduling, which is going to be a way to encode iteration in non-uniform convergence. So let me show you how that works. So if I have these two vertex programs running concurrently, perhaps in a single iteration of the BSP model, they, during the scatter stage, can trigger computation on adjacent vertices. And so at some other iteration, perhaps again in the BSP model on the next iteration, or in an asynchronous execution, as processing resources become available, the computation will then shift to those vertices that were triggered in the past. And this actually becomes a very powerful way to encode both the focusing of computation, so the user-defined logic can then assign computational resources where they're most needed, but also to directly encode iteration at the level of vertices in our graph. Now what's kind of neat about this is by actually changing the schedule in our asynchronous execution from a FIFO to priority or to round robin, we can actually get very different behavior of both the algorithm and the system. This becomes a way to explore the role of scheduling in the execution of these systems. And then finally, we think about the Gibbs Sampler. We had this issue of consistency. And so the GraphLab abstraction actually automatically enforces a range of different consistency models, including snapshot isolation and strongly serializable executions. Snapshot isolation would correspond to a BSP execution. And then maybe running asynchronously, we might enforce a serializable execution. And in fact, by enforcing a serializable execution, we automatically get a convergent Gibbs Sampler. Now what's kind of neat here is that we had actually multiple ways to achieve these serialization guarantees. Things like chromatic scheduling, which use graph coloring to enforce serialization, or things like distributed locking protocols, which allow us to have an asynchronous schedule and still preserve these serialization guarantees. And again, the user doesn't have to reason about this distributed locking. It's automatically enforced by the abstraction in the underlying system. So it's pretty powerful. The GraphLab abstraction actually turns out to be able to express a wide range of computational tasks. So on top of it, we and many others contributed toolkits that can express algorithms for graph analytics, computer vision, and even collaborative filtering on top of this simple programming abstraction. And so now I want to talk a little bit about the design of the system we built to execute that abstraction at scale, so the design of the GraphLab system. And so here we had to answer the question, how are we going to partition and execute these vertex programs on very large real-world graphs? But to answer that question, we need to know what real-world graphs look like. And so one of the key characteristics or defining characteristics of many real-world graphs is this power law degree distribution. So here I've plotted the degree of the vertices against the number of vertices at that degree in log-log scale. And this is for the AltaVista web graph, but all of the graphs I look at would have the same characteristic picture. And so what we see is this linear trend with a negative slope alpha of 2, and then most of the graphs are around 2, which characterizes these power law degree distributions. And one of the key characteristics of that is that on the far right, in this graph, we have 1% of the vertices adjacent to 50% of the edges in the graph. So what we have is a very small set of high-degree vertices. And this is going to present unique challenges as we try to partition these graphs. So you get an intuition of what these graphs look like. It's better to think of them as more star-like. So you could have something like an ostensibly popular person at the center. That's Justin Bieber. And his many followers along the boundary. Right? So this is kind of the picture to have in your mind as you think about these power law graphs. And so if you look at this picture, you start to ask, how do I partition a graph like that across machines? Because that's necessary to get an efficient distributed execution. So if we think of our power law graph, our star graph, if I try to evenly assign my processors to each of my machines, you see I'm going to have to cut half the edges in this star graph. So it seems difficult to partition these. And actually, there's theoretical results that show that these power law graphs do not have good low-cost balanced cuts. And the machinery designed in scientific computing for partitioning graphs at scale perform poorly on these graphs. So we and many others adopted an alternative strategy for partitioning graphs, a very simple one. We would go ahead and just randomly assign vertices to machines and then hope that the number of edges crossing the cut was small. And if we closed our eyes, maybe it wasn't so big. But if you look at this picture, it's not looking great. And you can actually do a very simple calculation. You can calculate the fraction of edges cut as a function of number of processors. And you see that if I have 10 machines, I'm going to cut 90% of the edges in my graph, an expectation. At 100 machines, I'm cutting 99% of the edges in my graph. So it turns out this is actually a randomized algorithm for max cut. It's precisely the worst thing I could hope to do to partition this graph, right? But this is what I was doing. So we needed something better. And so we came up with perhaps a simple alternative solution, which really respects the structure of these power law graphs. And this is the solution. Rather than thinking about cutting graphs across edges, we cut graphs across vertices. So I'm going to split my high-degree vertices across machines in my cluster. And then I'm going to leverage my programming model to allow me to program for this original graph, but then execute it equivalently and efficiently in this transformed graph. So that's kind of the key idea in the power graph or GraphLab system. And so let me show you how that works. So normally we'd think of these graphs, these high-degree vertices, living on a single machine, having access to their adjacency information. But by adopting this vertex cut model, we're going to allow ourselves to split those high-degree vertices across multiple machines in our cluster. We'll nominate one to be the master and the others to be mirrors, and we're going to have to keep those consistent as that execution proceeds. And then we're going to go back to this gather, apply, scatter pattern and leverage the structure of computation. In the gather stage, we're doing a commutative associative aggregation over the neighborhood of the vertex. And that's something we already know how to parallelize across a distributed environment. In the apply stage, we're doing something that's inherently centric to just the center vertex, so it's vertex parallel. So that's something we could do easily on the master. And the scatter stage is something that operates just on the edges, and it's inherently edge parallel. And again, we'll respect this transform structure. So with that in mind, we can go back and look at the actual execution of PowerGraph or GraphLab on this transformation of the graph. So during the gather stage, the user-defined function g is executed in parallel on each of the adjacent edges of the vertex, and then partial sums are constructed on each of those machines, summing up just the edges on that machine. And then those partial sums can be shipped to the master to compute the final sum and to complete the gather stage. Then in the apply stage, we consume that sum, updating the property of the vertex using the user-defined function a. And then now in the scatter stage, we take that new vertex property, ship it to each of the mirrors, making them consistent, and then executing that edge parallel operation, updating Lagrangians or scheduling adjacent vertices to run at some point in the future. And so now we've found a way to decompose that computation of a vertex across multiple machines. And now the communication of our system depends on the ways in which we split a vertex across our cluster. In fact, it'll grow linearly with the number of ways in which we split that vertex. And it turns out there's a theoretical mechanism for cutting these graphs called a vertex cut, which would minimize the number of machines spanned by a vertex while ensuring work balance. And excitingly, percolation theory suggests that these parallel graphs have good vertex cuts. Unfortunately, that result is non-constructive, so they didn't give us a mechanism to construct these good vertex cuts. So we turned to a very simple heuristic, similar to our earlier result, or earlier technique that seemed pretty bad, but this time it's actually going to turn out to be pretty good. So we're going to take our graph, and we're going to actually randomly assign edges to each of the machines in our cluster, not vertices. So we're assigning edges to machines and allowing vertices to span machines. The first thing to notice is that we actually have a balanced vertex cut. That because I've evenly assigned edges, I actually have evenly assigned the work of the computation across my cluster. The next thing to notice is that my high-degree vertices are going to get split often, but there's a small set of those. As the degree decreases, the number of ways in which I split a vertex decreases. And my 1-degree vertices, the majority of them, will never get split. So this is respecting this power law structure. And that's kind of the intuition. We can actually do a slightly sharper analysis and look at the expected number of ways in which a vertex is split across our cluster as a function of the size of the cluster and the degree of that vertex. And treating the degree itself as a random variable drawn from this power law distribution, or in this case a zeta distribution, we can show that this can be related to just this power law constant alpha. So we can characterize the replication just by the single statistic of our graph. And so if we plot here, for the Twitter graph, the number of machines, the expected number of machines spanned by each vertex is a function of the size of the cluster. This is our predicted curve, and this is what we actually get for the Twitter graph. So our prediction is very close to what actually happens when we run the system on this type of computation. So we can then take this analysis and go back and compare it to that really bad idea we had before. We randomly assigned vertices to machines. And we can show that we can get an order of magnitude improvement in the overall, or order of magnitude reduction in the overall communication storage overhead of the system by exploiting this alternative approach to partitioning our graphs. That's a kind of a theoretical characterization. We can also look at how the system performs when we run it in practice. So we built the GraphLab system as a C++ API, optimized for both multi-core and distributed architectures, with a fairly simplistic fault tolerance model built around checkpoint recovery. And we can now execute this on a sequence of graphs. And I'll talk first about how it performs on synthetic graphs that are going to test this power law hypothesis. And then I'll talk a bit more about how it performs on real-world graphs. So first, I've plotted the total network communication against the power law constant of a sequence of synthetically constructed power law graphs. And as I move left on this picture, I'm going to have more of these high-degree vertices. And so the orange line at the bottom is GraphLab using this vertex cut. And then the other two lines correspond to the blue line of prego, which is an alternative system. It has some of these ideas, but uses an edge cut. And GraphLab using just an edge cut, so this alternative really bad idea. And we see already that the vertex cut approach is robust to these power law vertices. So it's robust to the high-degree vertices. And it has a substantial reduction in the overall communication. And then likewise, we see the same thing for runtime. So this is runtime, same systems. And we see again that the vertex cut approach in GraphLab is now robust to these high-degree vertices. So that's how it performs on synthetic graphs. And the next thing to ask is, what if we ran PageRank on a real graph like Twitter? So here we compare, again, the total network communication for GraphLab using an edge cut, prego simulated using Piccolo, and GraphLab using a vertex cut. And so we here see almost an order of magnitude reduction in communication and more than an order of magnitude reduction in the overall runtime. And the improvement in runtime is also in part due to a better work balance as we've more evenly distributed computation across our cluster. All right, so you can't do these kinds of talks without comparing against Hadoop. So let me talk briefly about how our GraphLab system compares against a Hadoop implementation of a particular task. So here we'll look at triangle counting. So we're trying to count the number of triangles passing through each user in Twitter. And this is kind of a measure of the connectivity structure, the community structure around each of our users. So this is a graph of 1.4 billion links. And a state-of-the-art result for solving this problem using Hadoop was able to solve this problem in 423 minutes. So that's counting 34.8 billion triangles. And this is actually a pretty good result. It got a factor of 2 reduction in the earlier best result. And it's an algorithm optimized for the Hadoop abstraction. Now we compare against GraphLab. GraphLab on 64 machines solved the same problem in 1.5 minutes. So it's 282 times faster. There's a lot of reasons it's faster. GraphLab is a C++ API. This code was on top was implemented in Python, although they had 1,500 machines. GraphLab has some additional optimizations in its communication flow. We had a well-provisioned cluster. The Hadoop results running on Yahoo cluster. What's actually more important, though, if you go back and look at what's going on, if you look at the implementation, in fact, the abstraction described for the Hadoop approach, they have this degree squared dependence. They're not exploiting the effect of these high-degree vertices, whereas GraphLab is able to remove that degree squared dependence in the communication. So that's a comparison. Maybe a more fair comparison is we go back and look at a real machine learning system and look at how our general purpose framework compares. So if we look at the Gibbs sampling, the problem I talked about earlier, and we try to reason about the topical distribution of words and documents in the Wikipedia corpus, we're going to reason about 500 million tokens, and we're going to embed them in a 10,000 dimensional space. Now, a state-of-the-art result for solving this problem was developed at Yahoo over several months by a group of engineers, and they were able to process 150 million tokens per second. This is a pretty big result, it's a landmark result. When we compare with GraphLab, we're not as fast, so we can process 110 million tokens per second. But the key point here is we're able to do this implementation in just 200 lines of code in 4 human hours right before a conference deadline. I should say, right before a conference deadline, you should multiply that by like 5 or something if it was normal time. But still, less than a collection of engineers over several months. Right? So this is a substantial improvement in human efficiency, which is kind of what we seek with these high-level systems, to be able to be fast, but also to reduce human time it takes to build a fast implementation. So GraphLab was pretty successful as an open source project. It became one of the standards for graph computation and one of the standards for machine learning at scale. A lot of papers now compare against them, and even the ones I submit, the blind reviews, say you must compare against GraphLab, which is frustrating. So we've had a large number of toolkits built on top of it. And as a consequence of toolkits like collaborative filtering, we were also able to launch a company, GraphLab, now called Datto, which has actually taken this technology and deployed it in other real-world companies to solve real-world problems. So GraphLab has had both substantial open source and industrial impact. But maybe more importantly, GraphLab taught us something pretty neat. It showed us how to go from common patterns in machine learning to build abstractions that capture the structure of those patterns, and then build systems to execute those abstractions at scale. It allowed us to then separate the design of algorithms and systems. Before we had to publish these things together. Now we can think about publishing in a systems venue, describing the system, and in separate venue discuss the algorithms and how they map to that abstraction. As we go to optimize a system for one application, we actually are optimizing it for many. So improvements we made in the communication layer of GraphLab would affect all of those toolkits on top of it. So it's a much more scalable way to improve the design of machine learning systems. And maybe most importantly, it actually allowed us to accelerate research in the design of machine learning algorithms, of large-scale machine learning. In particular, it allowed us to compare these different trade-offs between consistency, between snapshot isolation, between different scheduling protocols, all in the same system, and being able to look at standard metrics like communication, runtime, as well as time spent in scheduling and messaging queues, as time spent doing useful computation. Right? So this became a very good way for us to explore the design of machine learning algorithms. All right, so I've talked a bit about how we designed algorithms and how that led to the introduction of abstractions and then systems for graph computation. And I want to step back and think about how graphs fit in the greater context of analytics. So in particular, how we think about graphs in the data processing systems. So far, we talked about how we might go from a social network to estimating the political bias of users. And now I want to think about the bigger picture. Where does our social network come from, and what do we do with the results of these political bias estimates? And often, as much as I like graphs, the data doesn't start out as a graph. It starts out perhaps as tables or unstructured data. It might be that I get posts and their classifications and the retweet information. And from that, I have to induce a graph. And then after running this graph computation, the end user doesn't care about a graph. They just want a table describing the properties or predictions of those users. And in this scenario, we have both tables and graphs, and we're trying to reason about multiple views of the same data. When we think about systems today, this is really addressed using separate systems. We have systems for tables like Hadoop and Spark, and systems for graphs like GraphLab. And having separate systems can be, one, difficult to use, because users must learn, deploy, and manage multiple systems. And this can often lead to brittle and very complex file interfaces across these system boundaries. And even worse, it can be inefficient, because we have extensive data movement and duplication across the network and the file system. Believe it or not, people are using HDFS as a communication protocol between Hadoop and GraphLab, storing each of their results in triplicate in a redundant file system. And actually, in this example, we're continuously building up and tearing down the same data structures. The kind of things we use to transform our graph in Hadoop are the same kinds of data structures we're going to then build again in GraphLab to compute on that graph. So this is very inefficient. And so this led us to ask, how do we expose tables and graphs as views of the same physical data to allow the user to choose the best view for the task at hand, all while retaining the performance of each of the specialized systems? And to answer this question, we introduced GraphX. And in a sense, GraphX is going to embed graph processing within a distributed data flow framework, in particular Apache Spark. And to do that, we had to address 3 key challenges. 1, how do we store graphs as tables? 2, how are we going to express these graph operations, these vertex programming models, in the language of data flow operators? And 3, how are we going to preserve those optimizations we developed, these vertex cuts, these communication patterns? We developed these in the context of specialized graph systems. How are we going to bring those over to these general purpose frameworks? So I'll talk about how we address each of these in turn. So when we think about storage, we had to take this property graph, this natural representation of graph structured data, and we're going to actually encode it as a pair of normalized tables, or horizontally partitioned tables. In particular, we're going to take our vertex properties and store it in a vertex property table that's horizontally partitioned here across 2 machines. And then we want to adopt this vertex cut approach, which amounts to cutting our graph across vertices, which actually corresponds to horizontally partitioning our edge properties in a separate edge property table. And the particular placement of edges in this horizontally partitioned table will correspond to different vertex cut strategies. Okay, so that's how we represent a graph as a normalized pair of tables. And now to define computation against those tables, as we said earlier, can be very painful. And so what we do is we actually encode these or wrap these tables in a graph abstraction. And we give the user operators like take a graph, again, internally represented as tables, and return a subgraph, which is, again, internally operated or represented as tables. Where operations like from a graph extract a view of just the vertex properties. Again, no data movement or duplication, just looking at the view of the underlying vertex properties. And perhaps more interestingly, expressing the entire vertex programming model against this horizontally partitioned pair of tables. And so let me talk about the bottom one, perhaps the most interesting one, and how we can encode our graph abstraction against this representation. And again, all of these are going to be done by mapping to filter, join, map, and reduce. So if you look at GraphLab, the first thing we had to do in this gather stage is apply this user-defined function G to each of these things we call triplets, so each of these records, which consists of the source vertex property, the edge property, and the target vertex property. Now, since we've encoded our graph as a pair of tables, we're going to have to construct a 3-way join to recover this triplet view. And so to construct this triplet view, we're going to take each of our edge properties from our edge table, join it with the source vertex property, updating or attaching the source vertex, and with the target vertex property, attaching the target vertex. So we now have a triplet consisting of source, edge, and target vertex properties. And we're going to do this for all of our edges in our graph. And I will claim now that we can express the entire vertex programming abstraction as a sequence of MapReduce jobs on this triplets view. And so let me show you how you do that. In the gather stage, we're going to simply construct this triplets view, apply a map, computing that statistic, and then a reduce, computing the aggregate. The result of that will then be joined back with the vertex properties, and a map operation will be applied, updating that vertex property. Then, now we've updated the vertex property, we've also updated the triplets view, and so we can finally execute the scatter operation as a map on each of those triplets. Now, if we did this, and we did in GraphX, it would be just 16 times slower than running against GraphLab. So while we now have a way to represent and encode computation, it's nowhere near efficient. So the remaining challenge is how do we get back that efficiency? And so to do that, we're going to go and distill the kind of ideas we had from GraphLab into this general purpose framework. So what was going on? So I have this edge table, and when I run this in Spark, I'm constructing this 3-way join, attaching vertex and edge properties. And the way Spark is doing this, the data flow framework we used, is through shuffle joins. The way that works is we take each of our edges, and we're going to key by the source vertex, which means we're going to partition each of the edges so they're grouped by source vertex ID. And then we can partition the vertices by vertex ID and complete the first half of the join. Now we're going to take each of these partially completed triplets, rekey by the destination vertex, and then shuffle again by the destination vertex. That was a hard animation. So all right, now we've got the destination vertex keyed. We can finish the join once more. And now we've constructed our triplets. But in this picture, we've moved the vertex and edge properties multiple times. In fact, we've moved the edges twice. When we have these large graphs with order of magnitude more edges than vertices, or often multiple orders of magnitude more edges than vertices, this can be really inefficient. So if you're a database person, you might say, well, a more efficient way to deal with this high cardinality, low cardinality join would be to use something like a broadcast join strategy. In a broadcast join, I'd send all of the vertices to each of my edge partitions. Right? Now, unfortunately, fortunately, my graph is pretty sparse, so I often didn't need that amount of data to move to each of these vertices. So I'm not exploiting the graph structure. In this picture, I only needed half the vertices on each of those partitions. So we had a very simple alternative strategy, which we called a multicast join, in which we encode or we build an index or routing table, which describes where each of the vertex properties are needed to complete this join. So the vertex A is needed by both machines, and so the routing table encodes that we need to send that to both those machines. Whereas the vertex property B is only needed by one of the machines, and so the routing table tells us that it only needs to be shipped to that machine. And what's actually kind of amazing is with this routing table, we can go back and implement this join as a shuffle join, keyed not on the IDs of the vertices, but on their join site, on the location in the routing table. And that'll actually give us something that's communication equivalent to the GraphLab abstraction, all on top of a shuffle join system. All right, so now we've completed our join. We actually, to finish the join, we ship the vertices to a local index on each of these machines, and now we can scan the edges and probe that local index to complete that final join. Now that local index actually acts as a cache, because we're going to support iterative non-uniform convergent computation. When we make a change to just a few of the vertex properties in our iteration, we only ship those that change, and we reuse the entries in our cache from before. And this is going to substantially reduce the amount of communication required to express iterative graph algorithms in a data flow framework. So here we plot the execution of the connected components algorithm on the Twitter graph. As a function of number of iterations, I've plotted the overall communication. And so initially, as the component IDs of the vertices are changing rapidly, we move a lot of data across the network. By around the 7th iteration, the computation begins to converge. And so we use this cache heavily to reduce communication in subsequent stages. So this allows us to, again, maintain this triplets view very efficiently. So there's a range of other optimizations I don't have time to talk about around join elimination, lineage-based model of fault tolerance, and index reuse that allows us to do these joins more efficiently. But putting all these pieces together, we actually get GraphX to perform comparably, and in some cases slightly faster than specialized graph processing systems like GraphLab. And in many cases, order of magnitude faster than the general purpose framework when executing these graph computations. And so what's kind of neat is GraphX allowed us to unify tables and graphs, and it enables users to easily and efficiently express an entire analytics pipeline in a single system. And in fact, GraphX is now a core part of Apache Spark and is being used by real companies like Alibaba, who are seeing order of magnitude improvements in their production pipelines when compared to their existing graph processing systems. But more importantly, GraphX taught us something pretty neat. It showed us how to take these ideas that develop in the context of specialized systems like GraphLab and extract the essential ideas in those systems and pull those into more general purpose frameworks, in a way allowing us to understand better what we did in these special machine learning systems. OK, so I've talked now about the design of abstractions, or the design of algorithms that led to abstractions, graph processing systems, and how we generalize those ideas to the context of data flow frameworks. And I want to look forward to the design of learning systems in the future and where I think they're headed. So I'll talk about the design of interactive learning systems. So much of the history of design of machine learning and systems really focused around this story of how we take data and we go through this process of training to build a model. So taking things like user item ratings and learning some function that, given a user item pair, can predict the rating for that pair. And now we have to ask ourselves, what happens after we train a model? And so if we're honest in the machine learning community, we write conference papers, right? So the grand result of all of our modeling is to build a conference paper. But we have aspirations. We hope that maybe someday some company might use that model to write a report, or some scientist might use that model to predict a better strategy for their cancer research. But more often, we actually believe that these models are going to be used in some kind of interactive process to drive actions, to make decisions. So let me give you an example, or a set of examples. So suppose I'm at Amazon, and I'm trying to suggest the item a user might want right as they check out. I might use a model there to predict the kind of things you want to add to your cart right as you're about to check out. Or maybe you're at eBay, and you want to use a model to predict right as a bid is placed, is that a fraudulent bid? Right? We want to make these predictions quickly. Or you're at Apple, and you're trying to understand what the user is asking of your phone. Again, you want to make these predictions for that user in real time. Or you're a GE, and you're very interested in the Internet of Things, and you have a sensor network deployed in jet engines or in jet turbines, and you're trying to understand, are these about to fail? And you might want to choose to switch off a power generation turbine because it's about to fail. So in all these settings, we have this need for low latency, where we want to make predictions in near real time. We're often trying to personalize our predictions, whether it's for a person on Amazon or for an engine in the context of Internet of Things. We're trying to fit models not to everyone, but to specific contexts. And then we're not thinking about data that's static, but data that's rapidly evolving. People's interests are changing. The kinds of signals that indicate a jet engine might fail are also changing. And so we had to think about how we can build models to address each of these challenges. And if we look at what's being done today, it's actually a pretty limited set of approaches. So often when one of the strategies we use to serve models today is to try to materialize everything, in which we essentially pre-compute all of our predictions offline. So it works like this. I might train a model offline in my data center based on the data I collected last week. Then based on that model, I might actually render all the user item predictions I could possibly need, and then store each of those predictions in a low latency data serving system like MySQL. This is good because it brings down latency and simplifies my serving tier, because all I'm serving is pre-computed predictions. But of course, I probably only need a small fraction of the predictions that I materialized. And so I often materialize far more than I would really need. Perhaps a smarter strategy would be instead to build a specialized prediction service. Again, I'd probably train my model on some data I collected last week, but this time I'd ship the model parameters and the computation itself and build this one-off, perhaps very fancy prediction service that I would put in my serving tier. Now here I'm now doing complex machine learning in my serving tier, which often could introduce latency or at the very least complexity in my serving environment. But actually both of these have a bigger problem, and that is we've in a sense split computation or split learning into two stages. We have this offline stage where all of our learning is being done, and this online stage where we're really just focusing on prediction. And what we really should start to think to do is, can we split machine learning or use machine learning across both these stages, training and predicting in both the offline and online contexts? So we actually started doing this in the context of the Velox model serving system. This is a system to serve personalized models. And the way we do this is we think of our large model not as this big black box, but as a collection of smaller modeling stages. And we can split this personalized model at a particular stage. Here we split it at the very end. And we think of the left half of this model as a representation of the input, as a feature model. And this is something that's going to change slowly with our features. So this is something that we could leverage the high throughput batch-oriented architectures designed for training on large amounts of data. And the part on the right is this personalization aspect, the part that's unique to each of our users. And this is something that's going to change quickly. And so it's something that we want to both train and serve in our online serving environment. That we can use systems ideas like feature caching or approximate feature evaluation to bring down the cost and hide some of the latency associated with these sophisticated feature models. And then because we've simplified the online component, restricted our attention to just the aspects of personalization, we can now adopt things like online updates and active learning on this much more simplified view of online machine learning. And we've already started doing this, actually. In our early prototype system, we're already seeing order of magnitude reductions, prediction latencies in a system that's continuously learning as new data arrives. And so I think this speaks to a bigger picture, that we need to get beyond thinking about how we go from data to model to start to think about how we can serve actions more efficiently with lower latency, and how we can incorporate those feedbacks, those updates, to maintain models that are fresher, and how we can go through this cycle more continuously to keep our models up to date as new data arrives. And I think the kind of exciting work in learning systems is really looking at the top part of this picture. And I believe that the future of research in scale learning systems will be in the study of this larger machine learning lifecycle. And this really can only be done by thinking about the design of machine learning algorithms, abstractions, and systems. And with that, I thank you, and I'd be happy to take questions.
So as you pointed out, PageRank is an instance of the gather, apply, scatter model, right? And people at Google and elsewhere did a lot of work on scaling it up well before GraphLab. So why not start from that and see how to generalize it, right? Which in some ways seems to be what you ended up with after a long time.
Yeah, so I didn't have much discussion of the Google solution to this. So Google's solution to these problems was a system they called prego, which shares some similarities with GraphLab. We actually developed at the same time, or at least published at the same time. The prego system is really built around messaging. In many ways shares some of the ideas from scientific computing, where the user is controlling the movement of data and the computation. And And one of the things we wanted to do with GraphLab is take some of that control away from the user and allow the system to do some of those optimizations. Prego today is actually leveraging some of the ideas we have in the power graph system, like these vertex cut approaches. So they actually were sensitive to these high-degree vertices, especially when you think about high fan-out situations.
So in a large system, oftentimes the machine fail, and you would have to slow these machines. So how do systems actually cope with your situation?
So fault tolerance or stragglers, you say?
Both.
So first, how we do with fault tolerance, and then how do we do stragglers. So our solution to fault tolerance is or in the context of GraphLab, it was simple, and it worked well for what we needed. So our solution is checkpoint recovery, which is what's used in scientific computing. It's costly in that we have to stop the entire computation and recover with the loss of a single machine. What we found, though, is in practice, these scaled clusters we considered, which were on the order of 64 machines, failed so infrequently relative to the time of computation that was adequate. With respect to stragglers, and the partitioning strategy had a big impact in reducing the effect of stragglers, although we considered well-provisioned cluster. In a multi-tenant environment where we might have had to share a machine with perhaps some other workload that's maybe Hadoop and therefore consuming all of our resources, we would be more sensitive to stragglers. I should say, with GraphX, we address both those in a slightly more principled way by leveraging the lineage-based fault tolerance. So in the context of machine failure, we actually recompute the history of that vertex or the set of vertices lost up to that point. And in the case of stragglers, we can use speculative execution. Yeah.
Back in the 1980s, there was a parallel graph algorithm that were very popular in the theory community, and there was probably 1,000 papers.
Yeah.
How does that research relate to what you've done?
So we went back to that to a certain. So I should say there's a textbook from that grew out of that work, and we went over it as a reading group actually when Carlos was at CMU. And one of the things so it talks a lot about this asynchronous model, and so some of those ideas we pulled into our asynchronous model of computation. In terms of systems, it's interesting. I look back, there really wasn't this design of high-level systems around that work. There was this focus in the scientific computing community that was really geared towards performance, and the design of these high-level systems was, in some sense, not in that direction. I should say a piece of parallel work that we hadn't seen until later on in this project was something called combinatorial BLAS that came from the scientific computing community that builds graph algorithms around a matrix multiplication model, or a generalized notion of matrix multiplication. It's really, again, built around the MPI architecture, and in order to use it, you have to define everything in terms of MPI primitives. But it does try to lift that abstraction of graph computation up at least the level of sparse matrix multiply. And I think that's pretty cool. In fact, I'm collaborating now on trying to bring that work into the GraphX model as an alternative way to express graph computation.
Great. Let's thank the speaker then.
Thank you.